Hello, I am Seema and welcome to part 20 of the chapter Haloalkanes and Haloarenes. In part 19, I was telling you about asymmetry and chirality, what asymmetrical molecules are and what leads to asymmetry and how asymmetry in a molecule leads to chirality. In this video, we are going to move ahead with this discussion and I'm going to tell you a little more about chirality and I'll talk about enantiomers. Let us take this one molecule, that is Butane To All. This compound can be represented by a formula which is known as the Wedge and dash formula. And with the help of a Wedge and dash formula, understanding chirality becomes easier. In class 11, you have done the Wedge and dash formula. According to this, the central point is a carbon, the central carbon. The four bonds which lead from the carbon are shown by lines. The lines are the lines in the plane, that is the bonds in the plane, that is along the blackboard. And as you see, this is a wedge. A wedge is shaped in a way, is a dark solid wedge, and it seems to be coming out of the board. You know, when a solid thing, as something comes close to you, it gets bigger and bigger. Using that formula, a wedge is a dark solid line that comes out, and as it comes towards you, it grows bigger. So this is a way of representing so that you can show that this bond is coming out of the blackboard or the whiteboard towards you. And the dash, as something moves away from you, your view or visibility of it diminishes. So the dashes are used to represent, and the dashes go from a thicker area to a thinner one. So as the thing goes away from you, it gets smaller and smaller. So the dashes represent a bond that is moving behind the board. The lines, they represent the bonds which are in the plane of the board. The wedge represents a bond coming towards you, and the dashes represent a bond going away from you. Using the wedge and dash formula, chirality can be understood. So we take this first compound, that is Butane To All, and we represent it with the help of a wedge and dash formula. So Butane To All, taking carbon in the center, propane means it has 3 carbons, right? 1 carbon, 2 carbon, 3 carbons. So the central carbon in Butane To All, what is it attached to? If you take the central carbon, or let me just write the formula like this. Butane To All, CH3, CH2, CH2, okay, CH3, this will be CHOH because the all is on the second carbon. So this is your compound, that is Butane To All. So in this, you take the central carbon. This central carbon is represented by the joint here. And to the central carbon, what is attached? You see, to this carbon, you have one hydrogen, one OH attached, one OH. The hydrogen and the OH have been represented in the plane of the board. Then this methyl group is shown to be coming out of the board towards you, and this CH3, that is the other CH3, is shown to be moving away from you in the board. Now, we know a molecule would be chiral if it is asymmetric. If it has an asymmetric carbon or a chiral center, only then it would be chiral. And what is a chiral center? A carbon to which all 4 species that are attached, all the 4 bonds should have different constituents. In that case, a molecule is chiral in nature. And why is it chiral in nature, or why is it asymmetric? You can understand using this example. So there's a methyl group coming out of the board, and there's a methyl group going behind the board. And the 2 bonds which are in the plane of the board are H and OH. Now, if you make this molecule stand in front of the mirror, what you would be seeing is, what will you see? If I am standing, let us say I am the Butane To All. This is me, this is the hydrogen, and this is the OH group. They are all in the plane. Now, one CH3 is coming forward. This is my right arm, it is coming forward, and this is my left arm, which is going backward. So one methyl group is coming out of the board, one methyl group is going behind the board, right? But if I'm looking at myself in the mirror, this is the left hand. So the methyl group which is coming out of the board in the mirror image, in the mirror, is the left hand or from the methyl group is on the left side, and the one which is going behind the board or behind the plane of the H and OH is the right one. So the mirror image is actually flipped. Since the mirror image is flipped, whatever the right that was coming out of this image, that is me, the original structure, the CH3 was coming forward on the right side. In the mirror image, it was coming forward in the left side, and the other one was on the opposite side. Now, if you take that mirror image and you flip it, you just turn it, right? You take the mirror image. In the mirror image, it was the left hand which was coming out and the right hand which was going back. So in this molecule, let us say that the CH3 which is coming forward is the right one, and this CH3 which is going backward is the left one. In the mirror image, the CH3 which is coming forward would not be the right one, it would be the left one. And the one going backward was going towards this direction, is now coming towards this direction. So the left becomes right, and that direction has become opposite. Now taking this mirror image, now that mirror image which was there in the mirror, if you turn that image by 180 degrees, if you turn the mirror image by 180 degrees, I would suggest you stand in front of the mirror and try to do this. Imagine the mirror image turning, and when it turns, the hand which should be in the mirror image, the hand that was coming forward was the left one, because it is my right hand which is coming forward, and it is my left hand which is going backward. And in the mirror image, it was the opposite. So when you turn it around, you still have the right hand and the left hand that have become opposite. Now it will appear that the right hand is coming forward and the left is going backward in the mirror image. But both the groups which were coming forward and going back were identical. They were methyl groups. So now if you take this rotated mirror image and you try to superimpose, that is, place it over the original molecule, you can place it on the original molecule, because in here, after turning it around 180 degrees, you again have the hydrogen here, you have the OH here, you have CH3 here, and you have CH3 along the dash. So it is a superimposable mirror image. A superimposable mirror image means that this carbon is not asymmetrical. It has got symmetry in it. It is not asymmetrical, it is asymmetric, and it does not have a chiral center, and therefore it is achiral. It is not a chiral molecule. On the other hand, if we take another molecule now, that is butane to all. And in butane to all, we again make this structure, the wedge and dash structure. The carbon to which different species have been attached. So methane, now it is butane to all. So let us add CH2, CH3. Now this is butane to all molecule. This carbon is again the chiral center. You have a hydrogen, you have OH. We put the hydrogen and the OH in the plane of the paper. Now we show that the dashes, that is the methyl group, is moving away from you, and the wedge is this ethyl group. The wedge is coming in front of you. So the OH group and the H group are in the plane of the board. The CH3 group is moving backwards, and the ethyl group, that is C2H5 group, is moving forward. When you keep this in front of the mirror image of this molecule would be, it will flip. Everything on the left is going to turn towards the right. So OH comes here, H remains where it is, it stays here. The CH3 is again, it appears to be going back, but it is towards the, what was towards the right is now appearing towards the left. It is going back, and the C2H5 is coming in front. Now you take the mirror image and you flip it. Just turn the mirror image by 180 degrees, that is, rotate the mirror image. As I rotate the mirror image, imagine now again, as I'm rotating the mirror image, as I'm rotating it, what was coming forward will now be going backwards. Do you see this? if I rotated the mirror image, this hand was coming forward. If this is an ethyl group and this is a methyl group. That was the mirror image which showed the ethyl group coming forward and the methyl group going backwards. When I rotate the image, the ethyl group is now going backwards, because after all, I've only rotated the image. I've not rotated the person who is seeing the direction of the bonds. So the H and the OH are still there. The ethyl group was coming forward, the methyl group was going backward from this plane, but as you rotated it, the direction of the H and OH may have changed, but the ethyl group is now moving backward because I am still standing here. As you rotated the image, the ethyl group is now going backwards and the methyl group is coming forward. And now if I try to superimpose this image over this, I cannot. Notice here, you have the OH here, you have H here, but here also the same thing had happened. The two methyl groups had switched, but you cannot tell the difference because both of them were methyl groups, and since they are not different, both of them would have the same properties. But here the ethyl group is different from the methyl group, therefore now when you get the 180-degree rotation of the mirror image, this cannot be superimposed over the original one. You remember when I told you that these are two hands? I cannot superimpose them in the same direction, but they are mirror images. But if I rotate one, then you can superimpose it. When we rotate this mirror image, the mirror image, the rotated mirror image cannot be superimposed on the original molecule. That is, now when you try to superimpose this carbon over this, the OH comes here, the H comes here, but the C2H5 is now going up backwards and the CH3 is coming forward, so you cannot superimpose it. So this structure F is not superimposable or non-superimposable on structure D. Therefore, this molecule is asymmetric. It is not symmetric. And since it is asymmetric, it has an asymmetric carbon, it has a chiral center. Therefore, it shows chirality and it is a chiral molecule. Right? Having understood this, let us take a few more examples of chiral molecules. 2-chlorobutane. How would you identify? In your exam, you get a question, how do you identify a chiral molecule during the exam? You don't really have to make the wedge and dash formulae in order to understand this. Conceptually, it becomes clear why it would be chiral. When all four species attached to a central carbon are different, only then the molecule is chiral. If any two of the species are identical, the molecule would be achiral, it will not be chiral, and it would be symmetrical. There would be some amount of symmetry. Therefore, for a molecule to be achiral, chiral, you need to check a carbon in the molecule to which all four species attached to it, on all four bonds should consist of different components. That is what we will look for when we have to identify a chiral molecule. So 2-chlorobutane is an example. Draw the structure of 2-chlorobutane. You have a methyl group here, you have an ethyl group here. Okay, so this is, what are the four groups? This is a methyl group, this is chlorine, this is hydrogen, and this is an ethyl group. So around this carbon you have four bonds and all four species are different: chlorine, hydrogen, methyl, ethyl. Therefore, how would you expect this molecule to be? It would be like 2-butane to all. So it would be a chiral molecule. Now the next molecule is 2,3-dihydroxypropanol. For propanol, well, let me just change the structure a little to make bonding clear. For propanol, this should be a double bond and this should be a hydrogen, right? So this is CHO is for the ul, and 2, 3, for the second carbon you have an OH group, and for the third carbon you have an OH group. So we'll take this carbon to be the center, which has four different bonds. Let's see. This has CHO on one side, one species is H, one is OH, and the other is CH2OH. Do you see? All four species attached to this carbon atom are different, and therefore this is a chiral molecule. What is the chiral center here? The second carbon is the chiral center. The next example is bromochloroiodomethane. Bromo, what is methane? Methane is CH4. 3 of the hydrogens are substituted with bromine, chlorine and iodine. So this carbon now is attached to 4 different species: hydrogen, iodine, bromine and chlorine. Right? Imagine this again, I'll take this example. When you have a tetrahedral molecule like this, right? The blue and the black are in the line of are in the plane. They are like this, perpendicular. They are in a plane. If you see my book here, it is in one plane, right? And the pink bond is coming outside, is coming out towards you, and the purple bond is going behind, is going to the back side, right? Now, in the mirror image, what are you going to see? You're going to see the blue and the black in the plane. You're going to see the pink coming forward, of course, but actually, if you imagine this to be a molecule that you're standing here and you're looking in the mirror image, this will appear to be in the opposite direction. This will be coming forward, this will be going backward, but if you rotate the mirror image now, this one, the pink one, would be going backward and the purple one will be coming forward. And when you superimpose it on the original molecule, you will not be able to superimpose it. And such a center would be a chiral center. Therefore, when all 4 species are different, such a molecule would be a chiral molecule. So in bromo, chloro, iodomethane, you have hydrogen, you have chlorine, you have bromine and iodine. So this carbon is the chiral center. The molecule is asymmetrical and it is chiral in nature. The next is 2-bromopropanoic acid, another example of a chiral molecule. This carbon is chiral here, is the chiral center. It is attached to COOH group on one side, H on one side, Br on one side and CH3 on the 4th side. So all 4 sides, the species are different, therefore the molecule is asymmetrical. Since it is asymmetrical, it is chiral. The stereoisomers, now let us move on to I will be doing one solved example here before I wrap up the topic, but before that let us understand what enantiomers are. When you have isomers, that is one of these, if all of these are chiral molecules, then each of them has a mirror image which is non-superimposable over it. Even after rotating it, you cannot superimpose it. So they are 2 different stereoisomers. They are isomers of each other, but they are not isomers in physical properties. They have the same physical properties. The only difference is that the arrangement is different. Which molecule, which part is coming forward, which is going backward. In space, their arrangement is different. And that leads to a difference in their optical properties. That is, these 2 would be a pair of isomers. Such isomers are called stereoisomers. And non-imposable stereoisomers, that is non-imposable mirror images, and such isomers are known as enantiomers. So the stereoisomers that are non-superimposable mirror images of each other, they are called enantiomers. Enantiomers have the identical physical properties because the melting point, boiling point or solubility, refractive index, all these depend on the groups. They do not depend on the arrangement of the groups. The only property that depends on the arrangement of the groups is the optical activity, whether it will be dextrorotatory or would it be levorotatory. So the enantiomers, they differ only with respect to the rotation of the plane of polarized light. And that is, one of these isomers would be dextrorotatory and its mirror image would be levorotatory. Usually we do not know which one is dextrorotatory and which one is levorotatory. We only know that both of these are isomers of each other. We just put D and L, meaning that both of them have opposite optical activity. One of them is rotating the plane towards right and one is rotating towards left, but it may not be necessary that if I'm putting a D in front of this and a L in front of this one has to be levorotatory and this one has to be dextrorotatory. That is only done for convention. So this was about enantiomers and how they differ in their optical activity. Now we'll do one solved example. Give me a moment to write it down. Now this is example 10.8 of your textbook. The question reads, you have to identify the chiral and achiral molecules in each of the following. There are pairs, 3 pairs of molecules given to you. You have to identify which one of these is chiral and which is not chiral. What is the trick? Whenever you have the center, if you have 4 different species attached to the center, the molecule is chiral. If you have even 2 species which are identical, the molecule will not be chiral, or it will be achiral. So in order to know the chiral molecules, let us see what are the, this is the chiral center here. Okay, so if this is the chiral center here, what are the 4 species? You have OH here, you have H here, you have CH3 here, and Br here. All 4 species are different. Therefore, this is a chiral molecule. Look at this one. This has got H, Br, CH3. So Br and Br are identical. So this is achiral. Right? It is not chiral. This one would be achiral. This is chiral. Come to the next example. You have, this is your chiral center, and on the 4 groups that are attached to this chiral center are OH, H, CH3 and CH2, CH2, CH3, right? Do you see this? This is CH2, this is CH2, and this is CH3. So you have a propyl group here, you have a methyl group here, alcoholic group, and hydrogen. So this would obviously be a chiral center because all 4 species attached to the chiral carbon are different. Therefore, this is chiral, and this one has hydrogen, OH, and look here, this is an ethyl group, CH2, CH3. This is also CH2, CH3. So 2 identical groups, it will be achiral. The third example, you have 2 bromobutane and you have bromobutane, right? The bromine is on the 2nd carbon, here bromine is on the 1st carbon. Which one of these would be chiral and which would be achiral? Bromine, when it is attached to the 2nd carbon, let us see what are the bonds this carbon has. This carbon has 4 bonds, the hydrogen here. So you have bromine here, ethyl on this side, hydrogen on this side, and CH3. All 4 groups are different. Since all 4 are different, this is chiral. And here you have CH2. So let us expand the bonds of the chiral carbon, of the carbon, this carbon of your focus. 1 hydrogen here, 1 hydrogen here. Propyl group here, bromine here, but 2 hydrogens are identical. Since these 2 are identical, this would not be be symmetrical, or it is not asymmetrical, it is achiral. It will not be a chiral molecule. I hope with this it is clear what is chirality and what enantiomers are. The mirror image of a chiral molecule, a molecule which would be present as its mirror image, as its non-superimposable mirror image. These 2, the pair of molecules, one of which is the non-imposable super mirror image, non-superimposable mirror image of the first one, this pair would be known as a pair of stereoisomers or enantiomers. Stereoisomerism is are compounds that have the same molecular formula, but they have different, due to their different stereochemistry, they have different optical properties, and such isomers are known as enantiomers. With this, I'll wind up today's video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.